Hi everyone, this video is about the limiting sum of a geometric series under the topic of sequences and series. In this video, we will explore concepts such as what a limiting sum is, the limiting sum formula, and how it is related to problems involving recurring decimals. So, what is the limiting sum of a geometric series? Well, in simple terms, it is the sum of a geometric series that goes on infinitely. However, the limiting sum is only applicable to an infinite geometric series that converges on a specific limit or value. This means for the limiting sum to be applicable to a GP, it must adhere to the following condition. This is where the absolute value of R, which is the common ratio, is less than 1. This can also be written as R is in between the values of -1 and 1. The actual purpose of the limiting sum formula is to determine whether a geometric series with an infinite number of terms converges on a finite value. So, the formula for the limiting sum is quite simple and uses the same variables used in the formulas for geometric sequences. We can see that the formula is given by the sum of infinite amount of terms, so S infinity, is equal to A, the first term of the sequence, over 1 minus R, where R is the common ratio that lies between the limits -1 and 1. The following example asks us to determine the limiting sum of the GP, given by 16, 8, 4, all the way down to a half, and then continuously decreasing. To determine this, we must first identify any relevant variables. We can see from the sequence that the first term, or A, is equal to 16, and the common ratio of the sequence is half, as each term is being divided by 2 from the previous term. Now that we know these variables, we can substitute them into the limiting sum formula to find the finite value where the sequence converges. After completing the calculations, we can see that the sum of infinite values for the given geometric progression is equal to 32. Now, although the limiting sum formula and recurring decimals don't seem to have anything in common, we can see they both relate to geometric sequences. Recurring decimals are just GPs that continue infinitely, to a number so small it is essentially 0. As such, we implement the limiting sum formula to convert recurring decimals into fractions. For example, we see below the recurring decimal of 0.33 recurring. We can expand this decimal into the terms 0.3 plus 0.03 plus 0.003, continuing on forever. To convert this example into a fraction, all we would need to do is identify the first term and the common ratio of this geometric sequence and substitute values into the limiting sum formula. Let's complete this example. We can see that the example is a GP with a first term of 0.3 and a common ratio of 0.1 or 1 over 10. Now, substituting these points into the limiting sum formula, we can complete calculations to successfully turn the recurring decimal into a fraction. So here we see we start with the recurring decimal 0.33 is equal to A on 1 minus R. Now completing these calculations, we can see that the recurring decimal of 0.33 is converted into the fraction of 1 over 3. It's now time to approach a harder HSC test problem. The following question is from the 2008 HSC Advanced Math paper. The first part of the question asks us to determine what values of x does the series have a limiting sum for. To solve this, we must go back to the basic principles discussed in the geometric sequence chapter, as we need to find the common ratio of the sequence. The common ratio can be found by dividing a term by its previous term. So, we can divide 10x, which is the second term of the series, by 5 to get a common ratio of 2x. Now, we also know that the limiting sum formula can only be applied to a geometric sequence with the common ratio between -1 and 1. So, we create an inequality. -1 is less than 2x, which is less than 1, and solve it to find the values of x which the series is a limiting sum for. Thus we can see that the values for x that solve the problem lie between -½ and 1/2. The second part of the question gives us the value of the limiting sum and subsequently asks us to find x. To start solving this problem, we must write down all known variables. A equals to 5, so the first term of the sequence equals to 5. The common ratio is equal to 2x. And from the previous question, we know that the sum of infinity is equal to 100. Now, we can substitute all these values into the limiting sum formula to determine a value for x. After working through the algebra, we see that the series with a limiting sum equal to 100 has a value of x of 19/40.